Hi, everybody, and welcome to Thursday of week 6. So today we're going to talk about the RSA encryption scheme. So this is a different way to send secret messages, still using modular arithmetic, but using it in a different way from Diffie-Hellman. Okay, so here's a setup. Bob arrives on scene with an important message for Alice, but oh no, Alice is sleeping. And meanwhile, Eve is just walking around whistling. And so Bob can't just write down his message for Alice, because if he does, Eve will be able to just pick it up and read it as soon as he leaves. So luckily, Alice has left instructions. So she left a little sign while she slept saying, "Please leave messages in box. I am sleeping. M is equal to 1517 and E is equal to 11. So this M 1517, this E equals 11. This is going to be instructions for how you can encrypt a message to leave for Alice that only Alice will be able to read. Okay, so how is that going to happen? Well, we're just going to walk through what Bob does, and then we'll explain how Alice can read it. I should mention this is all taking place in Hawaii. There's a palm tree over here. And the reason this is taking place in Hawaii is because the Hawaiian alphabet only has 13 letters in it, I think, something like 13 letters in it. In particular, if we just use the 10 letters E, A, O, H, L, M, N, K, and I, we can form lots of Hawaiian words. And that's convenient because these match up with the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we're going to use that as the basis for our encryption scheme. So in Diffie-Hellman, what we did is we got a shared key, we got a shared secret, and then we used that to make a shift cipher. Here, we're going to do something a little bit different. We're going to directly encode messages using numbers, and then we're going to sort of change those numbers, and then Alice will be able to undo the change to read it. Okay, so Bob needs to tell Alice, Bob, who arrived urgently on the scene, he needs to tell Alice the word Kona. So I'm pretty sure this is a hot stock tip for Alice. He's telling her that Kona coffee is about to come out with a new flavor and be purchased by a big investor. So Alice needs to buy Kona stock ASAP. And so, okay, so to send that message to Alice, Bob's going to take the word Kona and then just use this table to replace the letters with numbers. So the K goes to an 8, the O goes to a 3, and the N goes to a 7, and the A goes to a 2. So now Bob just needs to send this number, 8372, to Alice. But he can't send just this number because then Eve will be able to read it. So he has to do something to sort of encode or encrypt this number first. Okay, so the first step I'm going to do is actually going to break it up into parts and encrypt each part. So he's going to break it up into 2 parts, 83 and 72, so the KO and the NA, and he's going to encrypt each of these separately. So he'll use the same sort of algorithm to encrypt each of these. This is related to the information that Alice left. So Alice left these 2 numbers. She left M is equal to 1517 and E is equal to 11. And so the way we break up this number, or this word Kona, we want to do it so it has less, so each of these 2 numbers we use has fewer digits than M. So we could have done like 837 and 2. That would have been another way we could have broken up and sent the message. So just as long as we can't send all 4 digits at once, though. We have to sort of use fewer digits than are in this number. Okay. And so then that's, what do these instructions M equals 1517 and 11 mean? Well, it means instead of sending 83 and 72, Bob should modify these numbers. And the way you should modify them is by taking 83 and raising it to the 11th power, and then taking that number and looking mod 1517. And then to send 72, instead of saying 72, first he should raise it to the 11th power, mod 1517. And so then the numbers that he's supposed to send Alice are the results. So 821 in this first case, and 1097 for the second case, for the second two letters. Okay, so he raises to the E equals 11 modulo M, which was 1517. So you can think of that E that Alice left as standing for exponent, and that M is standing for modulus, if you want. We'll think of them as standing for other, we'll think of that E as standing for a few things actually, but exponent is a good one to remember. Okay, so that's what Bob does. He does that computation, then he writes down those two numbers, 821 and 1097 on a piece of paper, and puts it in Alice's mailbox. Eve has gone right up on top of the mailbox, and she's holding her magnifying glass, and she can read these numbers. But the point is, these numbers aren't going to help her. These aren't the numbers Bob is actually trying to transmit. Bob is trying to transmit 83 and 72. So Alice is going to have to do something to translate these back. And it's not something Eve is going to know how to do. Okay. So later that day, Alice wakes up and she looks at these numbers and she knows what to do. And Alice has a large head. She's about to do some extraordinary mental arithmetic. So that's probably why. Okay, so Alice looks at this and she sees these two numbers. And the key thing that Alice knows that Eve doesn't is she knows how this number 1517, she knows how this factors. So in Diffie-Hellman, we use sort of a prime modulus. But here, this isn't the prime number. This is actually the product of two prime numbers. This is 37 times 41. And sort of Alice was the one who made that sign. She got to pick which number she put up here. So she got to, she chose the numbers 37 and 41, multiplied them together, and then wrote 1517 on the board. So we've talked about this earlier, but factoring in general is a very difficult problem. For Eve, if she just sees 1517, she doesn't know how to factor it. And in practice, what you should think is actually on a computer is you would multiply sort of primes that have tens of digits. And then sort of the number you would get would be also have tens of digits, and then it would really be extremely hard to factor even for a computer. Okay, but because, so what's Alice going to, so what happens? How does Alice use this information to decode? So, well, and what did Bob do? He took the number 87 that he wanted to send. 87 or 83. So he took the number 83 that he wanted to send, and he raised it to the 11th power, and then he sent that. So he sent 821. And so Alice needs to solve this equation. She needs to solve and find which value of x satisfies x to the 11 is congruent to 821 mod 1517. And then for the second string, so this will give her the KO if she can solve this. And then to get the NA, she's going to have to solve y to the 11 is equal to 1097 mod 1517. Okay. So this is an example of the discrete logarithm problem. And in general, well, okay, this is sort of a different type of, yeah. Let me just not say that actually. This is sort of like playing the same role as the discrete logarithm problem last time. I mean, somehow this is a difficult thing to do, to sort of figure out what thing raised to the 11th power is congruent to 821, and figure out what thing raised to the 11th power is congruent to 1097. I mean, sort of if you just brute force it, the only thing you see to try is just sort of just go through all the possible x's and raise them to the 11th power until you find one that satisfies this. But if you have to do that for every number less than 1517, that's going to take a while. Okay, but it turns out there's a quicker way to solve this. So the unique solutions are going to be given by raising 821 and 1097 to some other number d. And what is this d? Well, this is the multiplicative inverse of e. So e was 11. So it's multiplicative inverse of 11, not modulo 1517, but actually modulo phi of 1517. So this is Euler's phi function. So this is modulo the number of things that are co-prime, the number of things less than 1517 that are co-prime to 1517. Okay. Well, so why is that? So I'll say what D is in a second, but why does that work? Well, I start off trying to solve, let's just look at this first equation. I start off trying to solve x to 11 as congruent to 821 mod 1517. And so let me just raise both sides to the d power. So x to 11 to the D is congruent to 821 to the D mod 1517. So that's true. But then let me look at this part. So this x to the 11 of D, this is x to the 11 times D. Just pulling in the exponent. So pulling it down from the power, becomes multiplication. Good, and what is 11 times D? Well, 11 times D this is congruent to 1 mod phi of 1517. So that means it's equal to 1 plus sort of some multiple k, or I'll say q, some multiple q times phi of 1517. Okay. So I can write this as sort of x to the 1 plus q times phi of 1517. It's congruent to 821d mod 1517. Okay, and actually let me sort of break this up. This x to the 1 plus this, let me just write as x to the 1, which is x times x to the q times phi of 1517. And let me even write that as sort of x times x to the q, the phi of 1517. Okay, so I claim actually this part is equal to 1. So that's the important part. So then this just gives me x is equal to 821 to d mod 1517. So this is congruent, like, so this power is congruent to 1 mod 1517. Okay, so why? Well, in fact, this is basically Lagrange's theorem. So, and let's just do one case. So if x to the q is in z mod 1517z cross, so if this thing I'm raising to phi of 1517 is in this sort of group of invertible elements mod 1517, then this literally is Lagrange's theorem. Then I mean sort of the order is phi of 1517 of the group. So the size of the group is phi of 1517. And so that's what Lagrange's theorem says. Like Lagrange's theorem says, if I take something inside this group and I sort of multiply it together for itself this many times, which is what you're doing here, so the size of the group times, then you just always get 1. So this becomes 1. And then we really get x is equal to 821 to the d mod 1517, which is exactly sort of what I set up here. What I said is the way that Eve is going to compute what x is. Or so what, not Eve, what Alice is going to compute what the way Alice is going to compute what x is. Okay, so that's, and actually even if x to the q is not in z mod 1517 z cross, so I mean, nothing I've said so far tells you that x has GCD 1 with 1517, so it might not be invertible, but that's actually still Lagrange's theorem. If you work it out, you'll see it's still Lagrange's theorem plus the Chinese remainder theorem in general. So that's a good exercise if you're sort of curious to understand how this works better, to work out and see why this is sort of still Lagrange's theorem, even if x is not invertible, and the Chinese remainder theorem. But otherwise, you can just sort of take this on faith. And hopefully, it should be pretty believable for you, since you know at least holds for invertible elements. Okay, so that's the justification of why this works. But the point is, Alice only has to do a simple thing. She has to find, like, she has to know what a multiplicative inverse of e equal 11 mod phi of 1517 is. And then as long as she knows what this d is, though, then she just has to raise this to the 821 to the Dief power and 1097 to the Dief power, and she'll get back the thing she wanted. So, I mean, the key point is that Alice knows enough information to compute what D is. Because, I mean, somehow she was the one who chose what E is. So she chose E to be 11. And then the hard part of computing D is you actually need to know what phi of 1517 is. And so that's easy to sort of compute this if you know the factorization of 1517, and otherwise it's hard. But Alice chose this number, and she chose it by sort of choosing two primes and multiplying them. So Alice knows the factorization is 37 times 41. So she knows the Euler phi function, when she applies it, she just gets sort of phi of 37 times phi of 41, which is just 36 times 40, because these are both prime numbers. And that gives her 1440. Okay, and then she chose 11 exactly, so it had GCD1 with 1440. And then she knows how to compute the inverse using just the Euclidean algorithm. And using that, she can compute that the inverse is D equals 131. Okay, and so she does that. So she takes 821 and she raises it to 131. She gets 83. She takes 1097, the second number she received, and raises it to 131. She gets 72. And she uses the alphabet. She translates that 8 back into a K, this 3 back into an O, the 7 back into an N, and the 2 back into an A. She gets Kona, and now she knows what stock to buy. Good, so that's how RSA works. Let me just go through that one more time, so without the cartoons, and just spell out what the steps of the algorithm are. Okay, so the cool thing about RSA is somehow Alice has set it up so people can send her encrypted messages. Like, she just has to sort of make a few decisions at the start, and then people can send her encrypted messages without her having to do anything. So unlike Diffie-Hellman, where you sort of have to actively establish a secret key with each person who wants to send you a message, and then sort of you send a few characters, and then you probably want to reestablish that key again. Here in RSA, like, Alice can just sort of post on the internet, here's my information, here's my M and here's my E. Now you can send me messages. Okay, so how does she sort of find this information that people can use to send her secret messages? Well, she starts out by picking two big prime numbers, P and Q. So everywhere below, I'm going to sort of draw the information that only Alice, I'm going to color the information that only Alice knows in this kind of blue color. So she picks two, well, in practice, big prime numbers, but in our example, we did small ones, so we could sort of do the computations, P and Q. So in this example is 37 and 41. And then she takes those and she multiplies them together to get M, the modulus, which is P times Q. And so anything that sort of Alice is going to share publicly, I'm going to put in green. Okay, and then she computes the Euler's function of M, so the number of numbers less than M that have GCD1 with M. And she can do this because she knows the prime factorization of M. She knows M is P times Q. So this is phi of P times phi of Q, which is just P minus 1 times Q minus 1. And so in the example, this was 36 times 40, which gave us 1440. Okay, and some of the point of all of this is, like, this is a computation only Alice knows how to do, because it's hard to compute this phi of M if you don't know the prime factorization. And it's hard to compute the prime factorization of a really big number. Okay, so this is somehow the thing that Alice can do that Eve can't do. So once she knows what phi of M is, she just picks some other number, little e, that has GCD1 with phi of M. And the reason she wants something with GCD1 with phi of M is exactly so that she can compute the multiplicative inverse, little d. So even though she makes this little e public, only she can compute the multiplicative inverse, little d, because only she knows what she's computing at modulo. Like, of course, and it doesn't help you to if I tell you compute the multiplicative inverse of e, you need to know modulo what, and only Alice knows modulo phi of M, like, because she's the only one who knows what phi of M is. So she can do this, but other people can't, even if they know E and M, because they don't know phi of M. Okay, so Alice does that to get D, and an example, this gave her 131. Okay, and so now to summarize, she's made these choices and done these computations, and she makes publicly available this number M, the modulus, and this number E, which is called the encryption or public key. Okay, and then she keeps private the numbers she used to make those computations. So P, Q, and phi of M, those were sort of all, so P and Q were how she made this number M. She multiplied them together, and then she could use those to compute phi of M. And then once she computed phi of M, she was able to use, and she sort of had already just picked E. So she computed phi of M, then she picked E co-prime to it. And then she can compute D, the multiplicative inverse of E mod phi of M. And that D is called the decryption or private key. And so this is all of the information she keeps private. If she shares any of this information, so then some of this D is the only thing she's going to need to decrypt messages. But if she accidentally shared any of this other information, anyone else would be able to compute D as well. So she needs to keep all of this hidden still. Okay, good. But so that's all Alice has to do ahead of time. And then once she makes M and E publicly available, now Bob can send her messages, Bob or anyone else. So in fact, I've written it like I'm going to send her a message. So if I want to send her a message, I would first turn the letters into numbers. So we turned Kona into 8372. Then I want to break those numbers into sort of just chunks that each chunk should have fewer digits than M. Just because I want to sort of get a unique thing modulo M. In the example, I did 8372. I just broke it up as 83 and 72. But I could have broken up as 8 and 372 or 837 and 2. The only thing I couldn't have done is left is 8372. Because in the example, I only had 4 digits in M. Okay, and then I just take each chunk, X, and I compute X to the E, modulo M, and I send that to Alice. So in the example, we sort of did 821, which was 83 to 11 mod 1517, and 1017, which is 72 to 11 mod 1517. It's hard to sort of undo this computation if you don't know D. Like somehow, if you don't know this D that Alice knows, so if you're like Eve intercepting this, that's hard to sort of go find out which number when you raise it to the 11th gives you 821. So that's sort of why Eve can't just like figure this out easily when she sees these two numbers. Okay, and then, well, so Alice gets this information, 821 and 1017, and now she wants to decrypt the message I've sent her. So she just takes each chunk Y she gets, and she computes Y to the D mod M. And so this number D, this decryption key, this is the thing that Alice computed that only she knew. So in the example, this was 821 to 131. If you write that out, you'll get 83 mod 1517. And then the other one is 1017 to 131. That will give you 72 mod 1517. So these are the computations Alice did in that example. And then UK, she ends up with 83 and 72. Sorry, I wrote that wrong on the slide. She ends up with 83 and 72. That gives her KO and A, Kona, and she knows the coffee to buy, I mean the stock to buy. I mean, maybe she buys the coffee too and the stock. Okay, so that's how RSA public encryption works. I want to just point out one thing that's a very easy mistake to make. So especially since we just talked about Diffie-Hellman. So in RSA, you see the modulus M and the encryption key E. And then when you want to send something to Alice, you just take your message X, you sort of turn it into numbers, and then you raise that to the E. So you take X and you raise it to the E. So X is sort of your message and you raise that to the Eth power. It's easy to make a mistake when you're doing this because Diffie-Hellman sort of does the opposite thing when you're making your key exchange. So in Diffie-Hellman, you see sort of this number P and this other number G. And then when you're doing the key exchange, so not to send your message, but when you're just sort of starting the key exchange, what you send is G to the A. So somehow, like it's like A is the thing you picked randomly, but instead of doing A to the G, like you do G to the A. And so it's hard to sometimes keep that straight because sort of you're doing the opposite thing up here. Like here, E was the thing that's public and X is your secret message, and you're doing X to the E. Whereas here, sort of A is sort of the thing you're going to use to help build a Serge secret. And so the A is sort of the thing you picked, and then you're sending G to the A. Okay, so while it's easy to accidentally swap the base and exponent, because it's sort of different in these two things, in order to avoid that, I recommend the following mnemonic. So we use the letters M and E always in RSA. Oops. So in RSA, we use always the letters M for modulus and E for encryption. And in Diffie-Hellman, we always use the letters P for sort of the prime modulus and G for the primitive root. And so you can remember that G stays on the ground. So G is always the base of the exponent because it stays on the ground, whereas E is an exponent. So E appears in the exponent. Okay, well, anyway, that's helpful for me to not get it confused. And of course, the best way is always to just think through about what's actually happening, and then you'll understand. But in a pinch, if you just need to remember what's what, this is a good mnemonic. Okay, well, anyway, we'll get some practice sending message with RSA in class on Thursday, and I will see you there. Thanks.